Hello everybody, I'm your host Hywel, and I'd like to welcome you to The Space Industry by satsearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello and welcome to the episode. Today I'm joined by Michael Seidl, Systems Engineer for Space Applications at Texas Instruments. As you probably know, Texas Instruments is a global manufacturer of semiconductors, integrated circuits and other electronic components, and has headquarters in Dallas, Texas, in the US. Michael himself is actually based in the company's European headquarters in Germany. The company also has a suite of products for the defense, aerospace, and space sectors. And today we're going to talk a little bit about how new space engineers in particular can balance risk, quality, and price, those three key elements of any mission, during component procurement. So thank you for being with us here today, Michael. Is there anything you'd like to add to that introduction?
No, thank you. I think you did a wonderful job. Thank you very much for having us here.
Let's get into this topic. Now, this is quite an interesting area and an area of challenge, an area that most teams have to consider. The new space teams are usually looking to get the highest cost of performance for components in their mission. Engineers want to keep risks low, have high quality and purchase at costs that are suitable for their needs. What do you think are some of the most important considerations for engineers who are looking to balance these three elements, risk, quality, and cost, when selecting components for new space missions?
In contrary to the traditional space market, in new space, cost is the very fundamental requirement, of course. So the total BOM must really stay here below a certain threshold to allow for a positive business case of the mission overall. Fully qualified space parts, as they are required for the geo or deep space missions, are simply not affordable in many cases. And in order to meet the cost targets, the manufacturers are then looking to adopt COTS parts and thereby assuming probably more risk for their mission that they really want to. And in response to this, TI has introduced its space-enhanced plastic product portfolio, the Space EP. So Space EP products address all the aspects of space requirements and make only very conscious compromises for the new space market to enable really the greater affordability. So let me highlight a couple of items of the Space EP product. So there's first of all, right, it's a real space product meant for space. Of course, it comes with a certain level of radiation hardness. So at least for 20K rad TID for every lot acceptance test. There's a one-time characterization for at least 30K rad TID. And the SEL characterization goes for at least 43 MeV. For the material usage, as said, is a real space product portfolio. There, we're not using any copper bond wires. All products will have gold bond wires inside. There is no high tin implemented. All the lead finish will be done with nickel palladium gold or any other finish that does not have pure tin inside, to avoid the tin whisker problem. And it also uses an enhanced mold compound to assure there's low outgassing, and there's also a very low moisture absorption in there. And for the general robustness, it of course covers a temperature range from minus 55 plus 125 degrees Celsius. There's also an extended qualification test for each assembly lot, including the HAST and also temperature cycling. Further, we're using for these products a controlled baseline with only one wafer fab, one assembly site, and one material set. And then in addition to all these, TI warrants also a very long product life cycle as it's typically needed in space applications. And for each of the products, we also provide the vendor item drawing, the VID, on the DLA website. So it's really a true space offer, just as the lower cost. And so it's bridging the gap between the commercial the COTS devices and the fully space qualified, many times ceramic packaged devices.
And so that's a really clear example there of the sort of weighing up the different factors that engineers are required to do. Now, you touched briefly on the qualification there of the material. And there are obviously various different ways in which engineers can qualify components which depend on the mission, the acceptable risk level, the volume of components and being used. What approaches to sort of screening and qualifying components do you think make sense in the different sorts of scenarios, space scenarios that you're dealing with, TI customers?
I think there is the very first most important question customers really have to answer for themselves is how much risk are they willing to accept for their mission, and also what actions they want really to take to mitigate it. Especially for the higher volumes, so if you're talking about hundreds or more of devices they need, then upscreening clearly comes to mind. However, upscreening at the component level is a challenging thing, and for a number of reasons, right? There's first, you have to get all the parts from the same lot, as there can be a lot of variability in terms of radiation performance from lot to lot. Within the same lots, then, you need to do further acceptance testing, as there can be radiation variability within the same lot, still from wafer to wafer and from die to die. And it can take a long time to find a part that really meets the mission radiation profile, and the cycle time for radiation testing can be long. So you might end up to test 3 to 5 different part numbers to find one that really works for you. So it can not only be very expensive to do the upscreening, but it can also be very time consuming. And further, then designers must really be aware that space qualification is not only about radiation hardness tests, right? There are also many other reasons for failures in space that must be mitigated by the correct packaging and material decisions. So many COTS devices will really exclude themselves from being a viable option for space, as they're simply not built the right way for it. Let me give you an example. So one of the main reasons that the plastic packages have been slow to be incorporated in space systems is that the packaging material is an organic mold compound, and that can absorb moisture and outgas organic compounds. So the moisture absorption can result in a reduced reliability and lifetime of the product, while the outgassing constituents, they can condense on other components, contaminating them and impacting their performance. So that's a major problem for the sensors, especially for the imaging sensors. And in response to that, TI Space EP products, they are plastics, right? But they are using a robust mold compound, and that is really also tested for outgassing acceptability and meeting the NASA standards, for example. And finally, another important criteria here for upscreening is, right, upscreening means that the parts will be monitored for functionality during and after the radiation tests. The semiconductor vendors now can take advantage of their comprehensive test programs that are part of their general product development and manufacturing efforts. So everything is in place there already. And except for rather simple products, the test houses do typically not have that convenience and the ability to perform testing with the full coverage as it would really be needed. So for highly complex devices, I would say it becomes fairly impossible to verify that truly no damage has happened to the device during any of the applied robustness tests without access to the original test methodology of the vendor. I think it's really one of the most important items, that the test coverage really has to be fully met.
Well, I wasn't aware that the radiation protection could differ within lots. Between lots kind of makes sense, but within lots significantly, that's a major issue. And as you say, if the impact of a lack of testing on those lots or the lack of acceptable radiation protection is that outgassing causes the component to affect the other components around it, could have a critical failure quite early on in the mission. So that's great. Thank you. I wonder if you could then move on to sort of providing a bit of an overview of some different NewSpace scenarios where some of these specific qualification approaches would be more applicable to teams than alternatives. How do they weigh up which processes to follow and which are not so effective?
Overall, TI provides 7 major classification levels, and let me explain those 7 levels to our listeners. The first 2 are called commercial and automotive, and those 2 are probably the most cost competitive, and they're really tailored towards all the high volume applications, and a flexible supply and guarantee supply is a key concern here. And the way this flexible supply is created is that each of these products here do typically have multiple manufacturing site options. And for each of the production steps, even from the wafer production and to assembly. And also the packages can use materials they shouldn't for space, like using medicine or copper bond wires, which are really not recommended for space. I'd say using these 2 classification levels for space applications come really with quite some risks. So designers should only use such products for their space missions if there are certain failure rates of these products is acceptable, and any outgassing would not raise any concerns to the components around them. And upscreening can only provide some level of risk mitigation, of course, but a lot of unknowns will remain here. So TI does not recommend to use commercial or automotive parts for space missions, really. Then there are 3 military standards, one called EP, which stands for Enhanced Product and uses a plastic packaging, and the other called QMLQ and QMLV, which come in ceramic packages. All three target the harsh environments and use explicit material sets for increased reliability. Further, all three provide a single controlled baseline, which means only a single wafer production site and assembly site is used to keep lot-to-lot variation low. However, they do lack any radiation hardness tests. Now, should designers use those to upscreen them? And I would say, well, in the absence of any affordable red hard component with similar functions, upscreening might be a thought here indeed, right? Especially for new space applications. At least you get some understanding of the sensitivity of these components towards radiation. However, the remaining concern would be the lot-to-lot variation and the most likely insufficient verification test capability. In other words, quite some level of uncertainty will remain after upscreening for these parts. And further, since these military components are more expensive than their commercial or automotive counterparts, designers need to analyze if upscreening would really pay off versus buying truly space qualified components then. So TI's recommendation for space is really the two remaining quality levels, and this is the Space EP and the QMLV RHA products. The Space EP quality level targets the LEO constellations, and they provide really a good balance between the robustness, the radiation hardness, and the cost, which is so important for new space. And the fully qualified QMLV RHA products are the right choice for any functions that are really mission critical or applications that will be exposed to higher levels or longer durations of cosmic radiation, as it would be the case for the MEO, GEO, or deep space missions.
You mentioned a couple of times now the assembly process for some of the components, from the idea of this have a single assembly process from wafer fab to assembly sites. But when people are purchasing or procuring components, deciding between different components, each has a value chain behind it. And there are many different combinations in which components can be realized within this value chain, from wafer fab to the final assembly site of the component and then into the subsystem. How much of a risk or quality impact can the semiconductor industry in general, have on different batches of components that are produced? And does space engineers, how much should they care about upscreening in this ecosystem?
Yes, this is exactly the challenge with upscreening, as semiconductor vendors cannot provide any guarantees on similarity between individual wafer lots with respect to radiation performance. This is the big difference between products created for space applications and those that target other markets. Especially for the commercial and automotive market, the supply flexibility is judged most important and much more important than keeping the lot-to-lot variations in radiation hardness minimal. Actually, it's not verified at all. And in manufacturing fabs, processes are continually monitored and calibrated to account for drifts over time that impact the electrical performance, right? That's what really matters in automotive and commercial. All these variations and drifts will be caught during the test and can then be rectified and will rectified into the foundry. But radiation performance will probably also vary with that. But for COTS and Q100 parts, there are no checks to see if the radiation performance is within limits or not. Therefore, you can see quite a bit of variability from fab to fab and also from lot to lot. And as said, in some cases, even from wafer to wafer. So if you upscreen, you have to make certain you get all your parts from the same lot and have a significant sample size across the lot to catch all outliers. And this is extremely difficult to do when procuring COTS parts, right? You have no idea where they're coming from. And from our side, it's like we say for products targeted for space applications, that is very different, right? There is a single controlled baseline, which means there is a well-defined set of materials used and only one wafer fab and assembly site involved. And for the quality level Space EP and QMLV RHAs, there is even a radiation lot acceptance test inserted here. And that really assures that any component leaving the door here is really meeting the desired radiation hardness.
Talking about radiation hardness, I mean, you mentioned the requirements for components that are going to be used beyond low Earth orbits, beyond LEO missions. And these sorts of missions and applications, even emerging commercial applications, are coming more into view for new space companies. I think they're more possible, and there's more of a commercial imperative to at least investigate them. The radiation considerations for devices used in those missions are obviously very, very important. In your view, do you think upscreening COTS systems to higher doses is going to become more of a viable option for shorter term missions beyond LEO? Say a 2-week lunar surface mission or something in GEO that's supposed to last for a couple of months or whatever it is. Or do you think this approach makes these missions too risky?
Let me put it this way. The way I see it is just the higher the level or the longer the duration a spacecraft is exposed to radiation, the higher the risk to experience a failure, of course. And therefore, customers ask for the higher radiation test levels for such missions. So the monetary risk in upscreening for any higher radiation hardness levels increases, and in several ways. First, chances are high that the COTS parts will simply not pass the upscreening, and the money and time for the test would be just lost. Or one would have to purchase and test components from several lots to finally identify a lot that passes, which of course means much higher cost and higher investment. And then second, if the upscreening was successful, still the coverage of the test program must be taken into consideration. Only because it passes the test house's verification test, it does not mean that the device does still meet all aspects and parameters as the semiconductor vendor would warrant in its datasheet. And since the launch for a higher orbit is always more expensive, a failure of a component does typically also have a higher impact versus a LEO application. So for higher orbits or deep space missions, TI only recommends full QMLV RHA parts. And since volumes are typically low, it is hard to see how upscreening would ever make much sense in such geo or deep space missions.
It's balancing those factors of risk and volume and price, and the volume is a key factor. Thank you. Finally, just to put your predicting hat on, I wondered if I could ask you how you see this question of risk, quality, and price, this balance of those three factors, evolving in COTS components in the next 3 to 5 years for new space missions in the industry.
Yeah, I would say is with the arrival of the intermediate quality levels, such as TI's radiation tolerant space EP portfolio, there is less motivation to go with upscreened COTS products. And I see there's definitely also a learning curve for both sides. So the design teams will learn about the impact of failing COTS devices in space and get clarity about where they can be used and where not. And likewise, semiconductor vendors continue to learn about the exact needs and will be able to further optimize the trade-off between required quality level and component cost for their customers. And the introduction of the Space EP is a very important step on this still young journey. And as the segment keeps growing, we can also expect vendors to optimize the cost per unit as volumes go up. It's the natural semiconductor business. Along those lines, we can then rather expect a decline in the motivation for upscreening of COTS devices as we go forward. And TI has clearly understood the need for more cost-effective radiation-hardened products and brought out its Space EP portfolio accordingly. Designers can expect many more products to be released in the near future in this quality level, as well as in the full Space QMLV RHA. TI is very convinced that space qualification is done best by the original semiconductor manufacturer. Only the semiconductor vendor has the necessary insights and the ability to control all factors, such as the technology node and design methodology, the used material set, or the manufacturing flow from wafer fab to packaging. And by applying its complete verification methods and test programs, quality assurance can cover all nuances of potential use cases. And last not least, it simply makes so much more sense to have the vendor run the tests once and support all interested customers with these results, instead of having each customer to finance and run his own qualification tests.
Yeah, makes a logical sense. And as we say, the balancing that cost is not just about the cost of the component, as you've explained. It's about the cost of testing, the cost of integration, and the cost ultimately of of a failure, of a potential failure. So I think that's a great place to wrap up, Michael. Thank you. Thanks, very much for sharing your insights with us. It's been really interesting discussion on testing, component choice, and covered quite a lot of the behind the scenes information from the manufacturer's or vendor's perspective as well, which I think is really interesting. So thank you.
Overall, so I hope I've been able to trigger some further interest in the TI portfolio. So if you're interested, or if you want to learn more about space grade components and technologies, please take a visit to ti.com/space, or please do also reach out to us, maybe via the E2E forum. We're more than happy to hear about what you're working on and see how we can support you best with our product portfolio.
Brilliant, thank you. And to all our listeners out there, please remember you can also find out more about Texas Instruments' portfolio of space components at the links in the show notes and on the platform at satsearch.com. And you can use our free request service to request technical details, documents, company introductions, quotes, information on lead time and export controls, or anything else that you might require for trade studies or procurement purposes. And finally, if you've enjoyed this episode, then please consider giving us a rating and subscribing wherever you get your podcasts today. Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.